What if the scariest part of the universe isn't that it's expanding, but that everything you've ever known is already being carried away right now without a sound? Because the Milky Way is not sitting in space. It's drifting, falling, and being pushed. And the most unsettling part is this. Even if we could map every galaxy we can see, there may still be forces shaping our motion from places we can't easily observe, hidden behind our own galaxy's glare and dust, in a region astronomers call the zone of avoidance. Tonight, we're going to answer one question in a way that actually changes how you picture reality. Where is everything in the universe going? And along the way, we'll uncover a truth that feels almost personal. You are not traveling through space like a passenger. You are inside a river, and the river has a current. For most of human history, the sky looked like a clock. The sun rises. The stars turn. The heavens repeat themselves like a promise. So it was natural to believe the earth was still, and everything else was moving around us. But science kept discovering a quiet pattern. When you zoom out far enough, nothing is truly at rest. Not the Earth. Not the Sunday. Not the galaxy. So, how do we prove motion if we can't feel it? Einstein's relativity tells us something humbling. Motion isn't measured against an invisible cosmic ruler. It's measured against other things. That sounds like it should make absolute motion impossible to define. But the universe gives us one extraordinary gift. A fossil light left over from the early cosmos. The cosmic microwave background. The CMB. It's everywhere. It surrounds us. And it's almost perfectly uniform. Almost. Because if you move through a sea of radiation, you create a subtle bias. One direction looks slightly hotter. The opposite direction looks slightly cooler. That pattern, the CMB dipole, is the closest thing we have to a practical cosmic rest frame. And it tells us something shocking. Our local group is moving through the universe at hundreds of kilometers per second. A speed so large it turns the word still into a myth. But that's only the beginning. Because once you subtract the obvious motions, the Earth around the sun around the Milky Way, there's still a leftover drift. A residue. A pull in a particular direction. And for decades, astronomers could only name it. In the late 20th century, astronomers noticed nearby galaxies weren't moving randomly. They shared a flow, like boats caught in the same tide. It looked as if thousands of galaxies were being drawn toward a hidden basin of gravity. But when they tried to look straight at the source, they ran into a cosmic blindfold. The zone of avoidance, a swath of sky obscured by dust and gas in the plane of the Milky Way. So the thing pulling us had a strange, almost mythical quality. It affected everything, but we couldn't see it clearly. That's why it earned its name, the Great Attractor. Modern surveys, using dust-penetrating wavelengths, radio, infrared, and X-ray, revealed that this hidden region contains massive structures, including the Norma cluster, also known as Abell 3627, located roughly 220 million light-years away. Not a single object, not a single monster. A region dense, massive, complicated, where gravity has been quietly adding up for billions of years. But here's the turn. The Great Attractor isn't the final chapter. It's a chapter inside a larger story. We like to draw borders around things. Continents, countries, solar systems. So naturally, we tried to draw borders around the largest structures in space too. We called them superclusters, vast collections of galaxy clusters and groups. But superclusters are messy. They don't have crisp edges. So, in 2014, astronomers proposed something beautifully physical. Don't define a supercluster by how it looks. Define it by where it flows. Like watersheds on Earth. If galaxy motions are converging inward toward a common gravitational basin, that basin defines a home region. Using galaxy peculiar velocities, Brent Tully and collaborators mapped our local flow and defined our home supercluster. Laniakea, a Hawaiian word meaning immense heaven. In that picture, the Milky Way is not an isolated island. It's a neighborhood. Inside a city. inside a continent, and the Great Attractor region sits like a deep gravitational low point inside that larger watershed. But even Laniakea isn't the largest influence on our motion, because beyond it lies something even heavier. If gravity is the sculptor of the cosmic web, then the biggest structures are the deepest carvings. One of the most massive structures in our wider cosmic neighborhood is the Shapley concentration, also called the Shapley supercluster, a region so enormous that its gravity influences galaxy motions across vast distances. And here's a crucial point. When astronomers compare the motion implied by the CMB dipole to what you'd expect from the Great Attractor region alone, there's a tension. It can look like the Great Attractor isn't quite great enough to explain everything by itself, suggesting additional large-scale structure contributes to the flow. This is where modern catalogs matter. Projects like Cosmic Flows compile distances and motions for tens of thousands of galaxies, allowing reconstructions of how structures tug on one another through time. This is not perfect prophecy, but it is something close to a measured map of the current. And the map suggests we live inside nested streams of motion. Local group dynamics, Virgo region influence, Laniakea scale flow, and beyond, even larger attractors shaping the direction of the tide. But then the universe reveals a stranger truth. Not all motion is caused by pulling. Some of it is caused by pushing. We talk about gravity like it's the only architect, but the large-scale universe is carved by contrast. Dense regions pull. Underdense regions don't just lack pull. They can act like a kind of gravitational negative space, a place matter flows away from. In 2017, researchers using reconstructed 3D velocity fields described a dramatic feature influencing our neighborhood. A repeller aligned with our bulk flow, a region associated with a vast underdensity. A void called the dipole repeller. The name sounds like science fiction, but the underlying idea is simple. If you live near a deep emptiness, everything around the emptiness tends to stream outward, not because the void has anti-gravity, but because there's less mass inside it, and the surrounding mass distribution shapes the flow. In the flow picture, your motion can be described as the combined result of a pull toward massive regions, like Shapley, and a push away from a large underdensity. So the Milky Way's journey is not a straight arrow toward a single target. It's a vector sum, a compromise between giants. And then, just when that sounds like enough, cosmology adds one more layer. Maybe some of the largest scale motions we think we see aren't fully settled. Occasionally, astronomers find hints of motion so large it feels almost impossible. One example is the controversial dark flow idea, an apparent coherent drift of galaxy clusters inferred using the kinematic Sunyaev-Zeldovich effect. Early analyses argued for a large-scale flow. Later results, most famously from Planck, did not confirm it at the claimed level. And debate has continued in different forms. That's not a failure of science. That's science doing what it's supposed to do. Argue with itself, until only the robust signal remains. But there's another kind of echo we understand much better. In the early universe, when everything was plasma, sound waves moved through the hot fog of matter and radiation. When the universe cooled and became transparent, those waves froze into place as subtle density patterns. We call these patterns baryon acoustic oscillations, the BAO. Usually BAO is detected statistically across huge surveys. But in 2023, researchers presented evidence for something dramatic. A possible individual BAO scale shell-like structure in the nearby universe, named Ho'olelana, centered near the Boötes region, with famous structures like the Sloan Great Wall lying within the shell. That claim is fascinating because it reframes the cosmic web as something with memory, not just random clumps, but fossil geometry, an imprint from a time when the universe was young enough to ring. And it reminds us, we are not only moving through space, we are moving through a structure built by ancient physics. But now we reach the most important turn in the story. The reason this video's question has a tragic answer, because even if we know where the current points, we may never arrive. Gravity builds. Over billions of years, It assembles galaxies into groups, groups into clusters, clusters into the architecture of the cosmic web. That construction feels like a promise. If gravity is pulling us toward the great attractor region, toward Virgo, toward Shapley, then given enough time, shouldn't everything eventually fall together? But the universe contains a competing rule. The expansion of space is not merely continuing, it is accelerating. And that acceleration is associated with what we call dark energy, often modeled in the same mathematical family as Einstein's cosmological constant. When the expansion accelerates, distance becomes a kind of trap. Beyond a certain point, galaxies recede so fast that light from them can never reach us again. Not because they break the speed of light locally, but because space itself expands between us. The consequence is heartbreaking in its quiet way. Only structures that are already gravitationally bound will remain together in the far future. Groups like our local group can merge internally. Clusters can remain islands. But supercluster-scale structures don't have enough time to finish assembling before accelerated expansion stretches the web apart. In that far future, the Milky Way's ultimate direction becomes less important than the fate of the map itself. The distant universe dims, then it thins, then it disappears over the horizon. And what remains is an island universe, a remnant of what used to be a richly connected cosmic world. So where is everything going? Toward attractors, yes. Away from voids, yes. But over the longest timescales, the deepest answer is this: everything is going out of reach. And that is the emotional truth at the heart of cosmology. The universe built a masterpiece, and then wrote a force into its equations that slowly erases the view. If you want, stay with me a little longer. Because in the next episode, we'll ask the question that follows naturally from this one. When the horizon closes, what does the universe still allow us to know? We aren't just searching the cosmos for meaning. We're racing the dark to keep what we can still see.